Dear students, please attend to these short descriptions. The content, the recorded content available in Dersa website is recorded in Persian, but all slides are in English. I will re-teach that slides in English in online classes. Okay? Therefore, you can use Persian version or English version in Dersa website. Where are you? Iraq or Iran? Okay. Oh, most in Iraq. Okay. I will share my screen to reteach the slides in English. Please try to understand the Persian language. It could be help you to communicate better in Iran. And also, we will try to learn Arabic to communicate proficiency with your dear students. Okay. In this semester, I will teach parallel processing for graduate students of computer engineering. This is all references. I have introduced 3 books in the recorded lectures. The first book, Introduction to Parallel Computing by Grama and Kuma. Both are of the legends of computer engineering. The second book, in year 1, 2018, from Rابط, Introduction to Parallel Computing. And the third one, a pioneer book for parallel processing, Introduction to Parallel Processing, from Behruz Parhami, another legend of computer engineering, especially hardware. Side. All of resources are available in Dersa. Almost all of course are based this book, Introduction to Parallel Programming from Grama and Kuma. We split the semester to 2 parts. This is full semester, part 1, part 2. In the first part, we concentrate or we focus on the theory side based on the grammar book. And in the second part, we focus on the programming. For programming, you do not need any programming background. We will teach from basic. Okay, you do not require any knowledge of hardware. We require a bit hardware, and I try to cover that in the content provided for you. Now I will talk about grading policy, how you can pass this course. We have 3 sections. The first and the second sections are about your homework, which are based on theory from grammar book. You could gain 50% of your marks, your final marks. 10 out of 20. Sorry, I can't speak Arabic. I can't speak Arabic. And 15% of your marks are belong to your computer assignment. Ten out of 20. Now you have 20 of 20. The full marks are available for you. Nice to meet you, Fars Naji. But I have another bonus mark. Your final exam, 4 out of 20, is your bonus. If you gain this mark, you can reach to the point 24 out of 20. Therefore, you have a 5 bonus point. I think you can easily pass this course with a great number. Now, you only can attend in final exam and fill your papers. Okay. The topic of this course is parallel programming or parallel processing or parallel computers. So the first question is, what is parallel programming or why parallel programming? To answer this question, we will start a short description of a sequential computer. Sequential computer. What is a computer? It's a computation machine. Computer is a machine to help us to rapidly solve the problems. But we must translate the problem to the language that computer can speak. For example, this is the problem, and we want to translate it to the language Zainab, of computer. The first step is to split the problem to the smaller one. We split the problem to the smaller one. Each section should be translated to the one of the computer instruction. Finally, we have a series of computer instructions that define our first problem or original problem. Therefore, in a sequential computer, we split our main problem to a set of instructions understandable with the target CPU. Could you understand? I try to speak slowly and use the simple words. Okay. Okay, you could replay this recorded session and use the Google Translate to translate the English words to Arabic. Yes, this session now is recording. Okay, we are here. We split a problem to a set of instructions. Now, a CPU or a processor execute this instruction one by one. First instruction are executed by CPU, then the second instruction are executed, the third instruction, and so on, till the last instruction. Are PDF available in Darsa? All PDF are available in Darsa. The PDF of all course. Okay, this is a sequential computer. This was good for the previous century. For the years before 2000. At that time, the problems were simple and small. We had several thousand of instructions that could be executed serially or one by one, first, next, 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 and next, to the end of the problem. But you can imagine a new set of problems for the years after 2000. The problems were complex and large. Several million instructions. Oh, WhatsApp group. Yes, we can create a WhatsApp group. Please, one of you accept the responsibility to create the group and add the students to that group. Then, please, that person. Yes, yes. Send a message in Darsa to me, and we send him or her my phone number to add me to that group. You, I think Muhammad Abdul Manaf, you could accept this. Muhammad Abdul Manaf, could you create a WhatsApp group? Thank you. And add all of students to that group. Okay. Back to our course. We are here. Now, in the modern days, we have a complex problem with several millions or billions of instructions. How we can execute these problems as fast as possible? One approach is to increase the speed of this processor. Increasing the speed of the processor. This processor is a uniprocessor. Uni 1. It means that this processor can execute one instruction at one time. One instruction, one time. This processor is called uniprocessor. Okay. If we have many instructions, one approach to execute them fastly is to increase the speed of this uniprocessor. For example, we have a CPU with frequency of 2 GHz. Increase the frequency from 2 to 4 GHz. This is one approach. But this is not the ultimate approach. We have several problems with this approach that will be discussed about later. Okay. To describe that problems, we first should explain some real-world example. Now, in next 3 slides, we want to mention an image processing application, image filtering, and its relationship with parallel processing. This algorithm is not fixed. The problem is depend to you. You may have as this example, have an image processing application or cryptography application or a physics application or a chemistry or in any domain of science or even gaming. Okay. First, we want to describe the matrix representation of a grayscale image. Thank you, Nazar. Nazar or Nazar? This is a sample image. An image composed of grid of small points. Grid of small points. Each point called picture element or pixel. Pixel or pixel element. Pixel is an abbreviation for picture element. Okay, this is my رقم. Okay, great. We have several rows and several columns. Number of pixels are number of rows multiplied by number of columns. For example, in a full HD image, we have 1920 multiplied by 1080 pixels. Several million of pixels exist in a single picture in full HD resolution. This is an RGB image, a colorful image. Each pixel have some of red, some green, and some blue. For example, this pixel, as you can see, is yellow. It has 93% of red, 91% of green, and 0% of blue. To quantify of this percentage representation, we use 8 bit for red, 8 bit for green, and 8 bit for blue. Therefore, a red part of each pixel could be from 0 to 255, and this is valid for green, and also this is valid for blue. I enabled your microphone, Farsnaji. Farsnaji. Okay, we continue our lecture. When you are ready, you can speak. Okay. This is an RGB image. An image that each pixel has a part of red, green, or blue. We can convert this image to a grayscale one. What is the grayscale image? This is. No. We will talk about filtering in the next slide. We do not focus on image processing. We want to show you that image processing has a great application for parallel processing. Okay. This is a grayscale image. Some pixels are black, some pixels are white, and are some gray levels between both. Maybe. Dear Mariam. No problem. Mariam, can I continue? Okay. As the talk in this slide, each pixel demonstrates by a number with depth of 8 bits. Therefore, we could represent the black, pure black with number 0 and the pure white with number 255. Okay. A 0 pixel, a gray level scale pixel, another gray, 0, pure 0, gray, a pixel with number 157, 157 is a light gray, and a pixel with value of 255, a full or a pure white pixel. The matrix that contains the pixel value associated with the corresponding pixel of the original image is matrix representation of that matrix. In a digital computer, we have or we show the image in this style, in a matrix form, in a matrix of the numbers between 0 and 255. Till now, we talk about the representation, how we represent an image in a matrix form to use in the computer. Now, we want to speak about the simplest image processing application that exists in the image processing book. It's called image filtering. This is the input image. Could you say me this image contains how many pixels? Yes. 1, 5. Higher number or higher digit represent the brighter pixel. How many pixels exist in this image? Okay, simply we can count the number of rows. 1, 2, 3, 4, 5, 6, 7, and count the number of columns. 1, 2, 3, 4, 5, 6, 7, 8, 9. Number of pixels equals with number of columns multiplied by number of rows. Great. Thank you, Mohammed. Thank you, Noor. Thank you, Ibrahim. We have 63 pixels in this image. Now, to filtering this image, we should multiply this image with another matrix that called mask, or sometimes called kernel. Thank you, Mariam and Marve. Mask or kernel is a smaller matrix, usually 3 multiplied by 3 or 5 multiplied by 5. Mask or kernel is a smaller matrix with these dimensions. We have many types of mask. Some masks are used to detect the edge of picture. For example, Sobel. Some masks are used to smooth the image. I think you mean median filter. Median filter or medium filter. Smooth the image. The value of the entries define the application of that mask. When all of the entries are 1 or a fixed number, in this case 1/9, we have a smooth filter. Okay. We kill in the screen to have enough space for the rest of the lecture. Okay. No, we should multiply mask by image. But how we must multiply? Okay, we should take this mask and add on the first part of the input image, as you see here. Okay, as you see here. Then we should multiply each entry of the mask by its corresponding entry in the input image. Next entry, next entry. Next entry, next entry. In this section, 1 multiplied by 1, 1 multiplied by 1 plus 1 multiplied by 1 plus 1 multiplied by 2 plus 1 multiplied by 2, 3, and 4. And for the last row, we have 3, 1 that should multiply by 8, 7, and 6. If we sum this value, we have 1, 2, 4, 6, 9, 13, 21, 28, and 34. Yes, this is a 3 by 3 matrix. The mask here in this example, mask is a 3 by 3 matrix. Okay, finally, we should divide 34 by 9. We can approximate this number by 4. And place the 4 in the center of mask kernel position. Replace the value 3 with a result of mask image multiplication and addition, which is 4 in this example. Next, we should okay, it's better. We do not access to our pen. Okay, 34 over 9 is 3 point. Let me use our calculator. Three 0.78. But in this matrix, we have only integer numbers. Integer numbers are 1, 2, 3, not fractional numbers. For example, 3.2. We do not have fractional parts. Therefore, we round this number to nearest number, which is 4, and place it here. Okay. In the next step, we should repeat this procedure with shift the mask a pixel to right and repeat one multiplication for here, a multiplication, 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 and the last multiplication, and add all the results together. And finally divide it by 9. Now we acquire the second pixel. No, Muhammad Said, Nazar Muhammad Said. This is the input image. This is input image. This is input image. This matrix represents the input image. This is the kernel, or this is the mask. The mask is to use to modify or to filter the input image. Mask is used to filter the input image. Mask is a small matrix. Mask could be 3 by 3, 2 by 2, 5 by 5, 6 by 6. But usually it's a 1-digit number. Okay, I repeat this example for the last position. Please attend. Please pay attention to this description. Okay, I take the mask, put it on the input image, and slide over all of the pixels of the input images, pixel by pixel, row by row, 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 till the end of the image. Finally, the kernel will be here. Finally, the kernel will be here. Now, how could compute the effect of kernel on the input image? 1 multiplied by 8, 8 plus 1 multiplied by 7 plus 7 plus 2 plus 7 plus 8 plus 1 plus 9, 2 and 1 equal with 17, 16, 33, 36, 42. Divide by 9. متوازية is equal with 4.67. That we round it to the nearest number, which is 5, and put it here. Okay. Thank you, Muhammad. Thank you first. This course is not an image processing course. We talk about this topic to show a great problem with many of intrinsic parallelism. To apply the mask on each section of the input image, we require 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 multiplication and 1, 2, 3, 4, 5, 6, 7, 8. 8 addition. Run to nearest. We have 3 major rounding policy. Run to up or ceiling, run to down or flooring, run to nearest. Here we use the run to nearest method. Okay, as you see, for applying the mask on each part of the image, we require 9 multiplications and 8 addition. To generate only 1 pixel of the output image. Only 1 pixel of the output image. Now you can imagine the size of the whole problem. The first of this slide, I ask you to compute the number of pixels available in this image. You say 7 by 9 equal with 63. Now, how many multiplications and additions we require to perform to applying this mask to whole of this image? Okay, simply we need 63 by 9 multiplication and 63 by 8 addition. Any question? Okay. But as you know, this is not a standard size of a typical image. An image contains millions of pixels. For example, Full HD image have 1920 rows by 1080 columns. And this is the number of all pixels of a Full HD image. Therefore, we require this number by 9 multiplications, more than 18 million multiplications, and this number by 8, more than 16 million of additions. Overall, we need more than 35 million of arithmetic operations, multiplication and addition. This is a great number. $35 million addition and multiplication for just a simple Full HD image. A simple Full HD image. Assume that this is your picture. If you want to apply a simple kernel on this image, you should perform several millions of additions and multiplications. How this huge number of arithmetic operation can done in this fast manner on the modern computers. This is the thing that available to us by parallel computers. Ibrahim, 63 multiplied by 8 is the number of additions performed to apply this mask on this input image. Okay, Ibrahim. Dear Fars, unfortunately, I don't have any link. The link I used is the link that you have. Oh, 63 is the number of pixels of the input image. Number of rows, 1, 2, 3, 4, 5, 6, 7. 7 rows multiplied by 9 columns. Oh, why 8? Okay. Number of additions is 1 smaller than the multiplications. Why? A multiplication, a multiplication, a multiplication, another, 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 and the addition operator adds between the multiplications 1, 2, 3, 4, 5, 6, 7, 8. Okay. Thank you, Muhammad. I understand. Thank you. Ibrahim, no problem. Oh, you should. Okay. Okay. We say that this is an example for parallel computation. Why? Why this is an example for parallel computation? Why? This problem, I mean filtering an image, is a good example for parallel processing or parallel computation. As we say, we apply the mask here. A bit later, We shift the mask to right and apply to the next position, and we apply the mask in the final position. And also we may sometimes be here to apply the mask in this position. The whole thing is behind the word dependency. Applying the mask here is independent of the applying mask at that position or applying the mask at this position. Okay, Nazar. Okay, thank you. Good. Mohammed, I cannot understand your meaning. Okay. Applying the mask at each position is independent of applying the mask at another position. Why this means? This means that when we apply the mask here and acquire a result, here is 4, we never use the number 4 in another steps. Oh, thank you. I see the parallel processing groups on WhatsApp. You added me. Thank you, Mohammed. Listen to the lecture or create the group. Okay. Therefore, we have several or many independent tasks. We have many different independent tasks. No, we could back to the CPU or uniprocessor discussed in the first slide. In a uniprocessor, execute task 1, then it executes task 2, then executes task 3, then executes task 4, and so on. we should perform in a correct order. First, second, third, fourth, and so on, to ensure of the accuracy. Why? Because the first task maybe generate a value that in the later steps used by task 2. Yes, you can watch it later. Okay? In a uniprocessor, the order is important. We should execute each task in a correct order. First task, second task, third task, fourth task, and so on. Why? Because we may have a dependency between the tasks. A dependency means that a task may be generate a result that could be used by the later task. Now, as you see, in this application, in these types of application, such as filtering the image, we have multiple or many independent tasks. Therefore, we can use multiple CPU. And assign each filtering, the green filtering to the CPU1, the red filtering to the CPU2, and the orange filtering to the CPU3. Yes, yes. Good, Nazar, good. The key point is the dependency. Dependent task can be distributed between the multiple CPU and executes in parallel. This is the work we will done in this course. As you know, do you know the CPU of your computer? Mohammed, can you say the CPU of your computer? Its model, Core i5, Core i7, it's Core i or previous generation? Core i5. Core i5. Okay. Core i5, Core i7, great. All are the state-of-the-art CPUs. Each Core i5 CPUs, you buy a Core i5 CPU. In fact, you do not buy a single uniprocessor. A Core i5 contains 2 or 4 uniprocessor. All modern CPUs are internally contains few uniprocessors. You could see my computer task manager. My computer has a Core i7 CPUs. This is my computer. Core i7 generation is 6. 6th generation U. As you see, we have, or I have, 4 logical cores. This means that in the modern days, when you want to write a program for your computer, you should learn parallel programming. If you write a program in the old manner, for the uniprocessor discussed in the first slide, you only use one of these CPUs and 3 others will be suspended. Okay? Okay. From the applications of parallel processing, we could mention video and image processing as the above example, machine learning, finite element physics, drug discovery, biology, financial transaction, chemistry, and so on. Very diverse application we could mention for the parallel processing. There is a website named top500.org. top500.org. No, Amjad, no. There are parallel. All have the same power and same application. Mohammed, you should try to write a good program that use all of the cores simultaneously or concurrently. A bad programmer write a program that only use one core. Okay, this is the top500.org website. In this website, you could see the top supercomputer of the world month by month. For example, the highest power computer at this time belongs to Fujitsu, a computer named Fugoku, or Fugoku supercomputer. What is Fugoku supercomputer? My computer has 4 cores. It's a Japanese name. But Fugoku has 5,630,848 cores. These are supercomputers, not personal computers. Personal computer. This is your computer. But supercomputer, this is a supercomputer, building size. Yes. For a very, very, very huge project. Okay. Now, I hope that this introduction was useful. Please take me a feedback about the quality of the presentation. If you have any advice, let me know. Okay. In the next section, in session 2 and its following sessions, in the series of slides, we will talk about the hardware. To understand some topics, same as course, physical or logical, about threats, about context, switching, and so on, we require a basic knowledge of hardware. I try to cover the basics, the minimal set of basics required to support the course in this series of slides. Do you have a course named Computer Architecture in your bachelor? خیلی عالی. I will teach you the necessaries in this slide. We start with a conventional uniprocessor, developed it, and finally we review the method used to increase the speed of the uniprocessors and finally we will discuss the problems of the available methods to increase the speed of uniprocessors, and in the last section we introduce the parallel processing to solve the problem, to a method to open a new approach. Okay, this is the topic of the last session, of the next session, online session. If you have any question, I'm available to you. I think in the next online class we could finish the hardware topics. I added the PDF in the class. الجلسة site here. Lecture notes are the PDF of all recorded slides. Why? Which is not clear? Oh, the original slides are on another computer. Okay, I will send the first lecture on the WhatsApp group. Okay, thank you, Essence. Okay. مراقب خودتون باشید دوستان. امیدوارم که در سلامت و عافیت باشید. خدا نگهدارتون.